Alright guys, tonight we're going to cover 3-3. This is going to be similar to 3-2, but we're going to take the information from 3-2, specifically the theorems and the postulates, and we're going to flip them. So 3-2 basically said that if two lines are parallel and cut by a transversal, then you knew that, say, for example, a pair of angles were corresponding. And if they were corresponding, then you conclude that they were congruent. Same side interior was supplementary, alternate interior was congruent, and alternate exterior was congruent. This lesson is taking that and flipping it. So now we know that the two angles are, say, corresponding, and that they're congruent. Well, then, because we know that, the theorems that we're going to talk about today or tonight is saying that the two lines are now parallel. So we're taking 3-2 and flipping it. The first two theorems I have listed on the screen, and I don't have the actual wording of the theorems. If you really want them, you can get them from the textbook. I just have the name of them and a picture to show you. I'll read them out, though, during the video, so that way you can just hear what they are. So the first theorem is theorem 3-4, and it is titled the converse of the corresponding angles theorem. This theorem says that if two lines and a transversal form corresponding angles that are congruent, and that's the key thing. Not only are they corresponding, but they must also be congruent. Then the lines are parallel. So if you look on the screen, you'll see that I have if angle 2 is congruent to angle 6, then we can conclude that line L is parallel to line M. So we're going backwards. The second theorem, theorem 3-5, is the converse of the alternate interior angles theorem. Sorry if you hear this squeaking, that's my dog playing with her toy. I will try to get her to stop in a second, but no promises. The second theorem, converse of the alternate interior angles theorem, says that if two lines in a transversal form alternate interior angles that are congruent, then the two lines are parallel. So I have an example here. If angle 4 is congruent to angle 6, then L is parallel to M. Now, for the converse of the corresponding angles theorem, you know that if one pair of corresponding angles in the diagram or the picture is given to be congruent, then all the pairs of the corresponding angles are going to be congruent. And then for the alternate interior angles, the converse of the alternate interior angles, we know that the interior angles that form linear pairs with 4 and 6 are also congruent. So we know that because they're both supplementary angles, they're also congruent by the congruence supplement theorem, which was from 2-2. Okay, the third theorem, 3-6, is the converse of the same side interior angles postulate. This one says that if two lines in a transversal form same side interior angles that are supplementary, then the two lines are parallel. So if the measure of angle 3 plus the measure of angle 6 is equal to 180, then L is parallel to M. Remember that the phrase same side relates to the same side of the transversal, either the right side or the left side. And so 3 and 6 are on the same side of the transversal, so these are our same side interior. The last theorem, 3-7, is the converse of the alternate exterior angles theorem. And this one says if two lines in a transversal form alternate exterior angles that are congruent, then the two lines are parallel. So if angle 1 is congruent to angle 2, if angle 1 is congruent to angle 7, then L is parallel to M. In the future, when you're doing proofs, you're going to have to either use the actual theorem itself or the converse of the theorem. And remember that if you're trying to prove that the two angles are congruent, or if the two angles are supplementary, then you're going to use the theorems from 3-2. If you're trying to prove that the two lines are parallel, then you're going to use the converse of those theorems. Really quickly, I'm going to introduce you to a flowchart proof. A flowchart proof is very similar to a two-column proof, except that the order and the layout that you do the proof is a little bit different. Instead of having the statements on the left side and the reasons on the right side, you're going to draw an actual flowchart or a flow proof, whichever you want to call it, in the boxes that you see on the picture and below, that's where you're going to write your statement, and then below that is where you're going to write the reason. So you have to make sure that it logically makes sense. On the quiz, some of you guys were answering the question and you were doing the proof, but logically it wasn't fitting together like a puzzle. And you need to make sure that you're doing that on here correctly. So that way when somebody else reads it, they understand how you got from point A to point B. For example, when you are making a peanut butter and jelly sandwich, first you have to take out the jelly, and you have to take out the peanut butter, and you have to get a knife, and you have to pull out the bag of bread, and then your next step is to open up the bag, and then your next step is to pull the piece of bread out. After you pull the piece of bread out, you have to open up the jar of jelly and the jar of peanut butter, and then you have to keep going and going and going. And if, say for example, I told the person to spread the peanut butter first, if that's the very first thing I said, then it doesn't really make sense. Because, well, how do they get the bread out? So you have to keep that in mind. Your proof has to logically make sense. For this particular proof, we're trying to prove theorem 3-7, and we start out with what we're given. So we know that angle 1 is congruent to angle 7, and that is given. That's our reason for that statement. We also know, based on the picture, that angle 1 is congruent to angle 3. And the reason for that is that vertical angles are congruent. So I'm going to abbreviate. Vertical angles are congruent. Because of those two statements right there, my next statement in my proof is going to be that angle 7 is congruent to angle 3. And I know that by the transitive property of congruence. Transitive property of congruence. And from that, I know that if corresponding angles are congruent, then their lines are parallel. So 7 and 3 are corresponding. I know that line L is parallel to line M because I do know that corresponding, oops, I ran out of room, angles are congruent. So there's my flow chart. You could have instead, if you wanted to, for where I put angle 3 is congruent to angle 1, you could have said that angle 5 is congruent to angle 7, and then the middle statement would have changed to angle 5 is congruent to angle 1. Either way, you would have a logical flowchart proof that it proves that if you know that angle 1 is congruent to angle 7, then L is parallel to M. Alright, here's an example problem just to kind of get you thinking. Which lines are parallel if angle 1 is congruent to angle 2? Justify your answer. In order to justify your answer, you would tell me the theorem or the postulate that you use in order to get your answer. Take a look at the picture. They told us something about angle 1 and angle 2. So the first thing is to figure out what three lines we're dealing with. Angles 1 and 2 are using lines A and B, and then line M. So line M is the transversal. A and B would be the two lines that were parallel if we have enough information. 1 and 2 are corresponding. They're created by a transversal, and we're told that they're congruent. So if they're corresponding and they're congruent, which means that A and B are parallel. So our answer would say something like, if angle 1 is congruent to angle 2, then A is parallel to B by the converse of the corresponding angles theorem. Really quickly, just one more example. Which lines are parallel if 6 is congruent to 7? Justify your answer. Tomorrow in class, I am going to have you guys answer this question at the beginning for your warm-up question, and I will check it to make sure that you did it, and that will count as a grade. So be prepared for that question. Okay, I'm going to briefly just talk about 3-4. There's three theorems on here. The first one is theorem 3-8. It doesn't have a name, but it says that in a plane, if two lines are parallel to the same line, then they are parallel to each other. So if A is parallel to B and B is parallel to C, then A is parallel to C. So we could mark these guys, A is parallel to C. Notice that I used 1 blue for A and B, 2 red for B and C, and 3 green for A and C. The colors don't really matter, but the numbers of arrows do matter. Think about how in real life, you could actually have this theorem really be used or be true. For example, where can you have two lines that are parallel, and if those two lines are parallel, then you know that they're parallel to the third line. You can pause if you want to, or you can just go ahead and go forward. Some examples are like supermarket aisles or striped shirts maybe, or even like the 5-yard lines on the football field. The next theorem is 3-9, and it says that if, let me flip my page, if in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So if M is perpendicular to T and N is perpendicular to T, then we know that M is parallel to N. And then for the last theorem, 3-10, in a plane, if a line is perpendicular to one of two parallel lines, then it is also perpendicular to the other. So if N is perpendicular to L and L is parallel to M, then N is perpendicular to M. So we can conclude that, on this last one, we can conclude that N is perpendicular to M. So in class, when we're working on these questions, these are going to be more application questions, word problem type questions that you're going to be doing for 3-4. Hopefully you will remember to come up with the answer to that question from 3-3 and bring that to class tomorrow. And I will see you guys tomorrow. Come see me in the morning if you have questions, or come see me after school or during a lunch. If you have B lunch, you can pop in if you want, but I have a class during that. Have a good night.